Dear students, welcome to the online teaching session of Wien's Bridge. Here you can see the schematic diagram representation of Wien's Bridge. This bridge is primarily known as a frequency determining bridge and is here described not only for its use as an AC bridge to measure frequency but also for its application in various other useful circuits. It may be employed in a harmonic distortion analyzer where it is used as a noise filter discriminating against one specific frequency. This bridge also finds applications in audio and high frequency oscillators as a frequency determining device. And here you can see a mechanical coupling between the first arm and the second arm. In the first arm, here we have a resistance capacitance combination in parallel. In the second arm, resistance capacitance combination in a series. And the third arm and also in fourth arm, we have only resistances. This bridge is used in AC circuits for determining the value of unknown frequency. So we should know how it is used for measuring frequency. So as we all know, the condition for balance is Z1, Z4 is equal to Z2, Z3. Z1 is impedance of the first arm. So in the first arm, here we can see the resistance and capacitance are connected in parallel. So this equal to the equivalent impedance will be R divided by 1 plus j omega CR. Here in the first term we have R1 and C1. Thus the expression becomes R1 divided by 1 plus j omega C1 R1 into Z1 into Z4. Z4 means impedance of both arms. It consists of only a single resistance R4. So this R4 is equal to Z2. Z2 is the impedance of the second arm. Here as you can see, the resistance and capacitance are connected in series. So the expression for impedance becomes R2 minus J by omega C2 into Z3 is the third arm impedance. It is a single resistance R3. So on equating real part and imaginary part, you can see on equating real part, it is equal to R1 R4 C2 is equal to R2 C2 R3 plus R3 C1 R1. So on cross multiplying, we will obtain R4 by R3 is equal to R2 by R1 plus C1 by C2. On comparing imaginary part, it is R3 R2 omega square C2 C1 R1 is equal to R3. So we can cut both R3s. So the expression becomes like this. From this, omega is equal to 1 by root of R1 R2 C1 C2. By substituting the value of omega as 2 pi f is equal to 1 by 2 pi root of R1 R2 C1 C2. And in the schematic diagram, the first and second arms of the bridge are connected mechanically. So R1 is equal to R2 is equal to R and C1 is equal to C2 is equal to C. Therefore, the equation becomes F is equal to 1 by 2 pi RC. Thus, we can find out the frequency of the system. Dear students, welcome to the online teaching session of Sheriff's Bridge. This is basic schematic diagram representation of a Sheriff's Bridge. The Sheriff's Bridge is mainly used for finding out the unknown value of the capacitance of a capacitor. Here in the first term, we see a capacitor C1, and this is a capacitor whose capacitance is to be find out. And here we have a standard variable capacitance C4. So a balance is achieved by varying this capacitance C4, and a null indication is obtained in the detector. Then we can find out the value of capacitance C1. And let C1 as the capacitor whose capacitance is to be determined. And here you can see a small resistance R1. R1 is a series resistance representing the loss of the capacitor C1. And C2 is a standard capacitor. Here you can see in the second term as C2, it is a standard capacitor. R3 is the non-inductive resistance. Then R4 is a variable non-inductive resistance connected in parallel with the variable capacitor C4. As we know, the general expression for balance in AC bridges Z1, Z4 is equal to Z2, Z3. Z1 is the first term impedance. Here you can see in the first term, resistance and capacitance are connected in series. So the impedance is R1 plus 1 by j omega C1. Then Z4. Z4 means 4th term impedance. This 4th term we have a resistance and capacitance connected in parallel. So the expression for impedance will be R4 divided by 1 plus j omega C4 R4 is equal to Z2. Z2 is the impedance of the second arm. So in this second arm, we have only a single capacitance. So its impedance is 1 by j omega C2 into Z3. Z3 is the third arm impedance. In the third arm, we have only a single resistance. So impedance is R3. So on equating real and imaginary parts, we get R1 as R1, small r1 is equal to R3 C4 divided by C2, and capacitance C1, its value is to be determined, is equal to C2 into R4 divided by R3. So these are the expression for capacitance and resistance. And the dissipation factor obtains with the help of phasor diagram of the Schrodinger's bridge. The dissipation factor determines the rate of loss of energy that occurs because of the oscillations of the electrical and mechanical instrument. Here you can see the phasor diagram representation. This here is one I1 is a reference and I1 R1 is here. This I1 R1 plus I1 by omega C1. Here you can see I1 by omega C1. These two, the resultant will give you E1 because here R1 and C1 are connected in series. So here you can see the resultant E1. E1 is equal to E2 when the bridge is balanced. Here E1 is equal to E2. E2 is I2 by omega C2. And here in the third arm, it consists of only a resistance. So it is I1 R3. Here you can see, here this one is your I1 and this is I1 R3. So it is E3 and E3 must be equal to E4 when the balance condition is achieved. Then this E1 plus E3 or E2 plus E4 is equal to E. You can see E3 and here this one E1. Okay. Then the resultant of this E3 and E1 is E. And the factor, dissipation factor tan delta is equal to omega C1 R1. So when we are substituting the values of C1 and R1, we will obtain D1 as omega C4 R4. Thus we can find out tan delta. These are the advantages of Schrodinger's bridge. Thank you.